Good evening, afternoon, morning, brunch, late afternoon, sunset, sunrise, whatever time, wherever you are. Hopefully, your day is going well. This is Architecture 530 Environmental Systems Lecture 8 Background Noise. So, we've got background noise, we have sound isolation, attenuation, and then we're going to do an analysis of sound isolation and then finish up, circle back around to analysis of background noise. But we want to start here. We want to go through some things to think about and consider, some items that we want to um, identify, be able to describe, avoid, um, and from a descriptive standpoint, be able to describe why um, something could be a problem before it is a problem. So, when we're talking about noise control um, in a system like this is your air handling unit on the left. We've got some ductwork with the diffuser, and this is conditioning this space. It's either providing heat or providing cooling, maybe taking out some humidity, maybe inducing some humidity in here. We're not worried about these three paths here. Everything on this side of isolation is noise isolation, sound isolation. So we're looking at this barrier here. Sometimes we would consider this ceiling a barrier, but if it's substantially less than this isolation, we don't consider that. We consider these black lines around here. This is why when I participate in crits and reviews with you guys, I really like to see the section, because when I'm looking at the section, I'm looking at the volume of the space. And from that volume from the previous lecture, I can get an idea of the reverberation. If you let me know what your materials are, I can start to visualize from an audio standpoint. Not audio per se, but sound, audiologically. Um, yeah, I butchered that word. I can start to see what that is. Likewise, when you cut your sections, I can start to see if you're going to have problems if you have a noise producing room right next to an acoustically sensitive room. So, what we're looking at in noise control is the breakout and break in noise here, this path one, and then what it is at the diffuser, this path here. So, we've got three things to consider. Unit type, we don't spend too much time on that. That comes from the mechanical engineer. Mechanical engineer is going to say how many air changes are needed here. From that determines what the unit is. We can make recommendations on what the sound profile is, but we can't say, yeah, we're putting less air. We're moving less air in this room. That's based on occupancy and use of the room. What do I mean by that? If this is 100 people and they're all playing basketball, your load's a lot more. If this is 100 people and they're all doing spreadsheets and they're setting at their office and there's not a lot of movement, the load's different. But then you also have the loads of the computer. So depending what the use of this space is, determines use and size determines what this unit is size-wise. From that, then it's the ductwork. Then we get the diffuser and the noises in the room. So let's take a look. So when we're looking at unit type, mainly what we're going to do is look at what's provided, run a calculation of what's provided, and see if we can get that to work. So the mechanical, when I say the mechanical engineer is going to lay out the ductwork, the diffusers, the throw, the air changes per hour, size the air handling unit, size the condenser, size the coils, and then from that data we're going to look at it. Every once in a while, if I know the mechanical equipment is going to be close to a acoustic sensitive room, I will forego backward curved and airfoil. So they just make a sound profile that's harder to it's a harder issue to tame on there. So these are spinning this way. A lot of times with efficient units, they're sacrificing on sound on them. Sometimes fan arrays are good, less static pressure. You're using um, less larger fans, but more of them. But this profile also is more of the upper end and not the lower end. Remember, the lower end's hard to control, anyways. So that's basically all we're looking at. We're taking the unit type that we're given from the engineer, and when we do sample problems or on the problems that you'll work out on your own, you'll be given the unit type. You just have to sift through the data to pull the proper data out to do the analysis. And then we have ductwork. So really, we're looking at the total length of the ductwork. We get attenuation for that. But really, we're considering what happens at this transition of isolation. And when we look at isolation, if we're isolating, we're putting an isolation wall here. We're doing some specialty construction to block this out. We don't want to be punching holes in it. Rule of thumb, for every 10 square feet, if you punch a hole of a square inch in that wall, you are probably short-circuiting that wall. So you might as well just put windows in it and actually just not build the wall, because you can get that noise into that space. So what do we consider with ductwork? Four attributes: size, type, length, material. So the CFM across the section of the ductwork, that determines the flow, the feet per minute of that air. Rule of thumb, you want to be at 350 feet per minute. You can get away with 800 in branch ducts that are in an acoustic sensitive room. But ideally, you want, if you're in your acoustic sensitive room, you want to be around 180, 200, 150 ideally, in that range. And it's a trade-off. Slower air means bigger ductwork. Bigger ductwork might mean less attenuation. Less attenuation might mean it's a little bit louder. Duct type, rectangular is better for attenuation, but increases turbulence. You increase turbulence, you increase static pressure. You increase static pressure, your fan size gets bigger. For circular, less turbulent, less absorption. So depending where you're putting that at, if you're moving a lot of air and you're moving it fast, might be better to run it circular first, break out on your branches, and move to rectangular where you're moving less air. It's much easier to get a right sized duct there, slow that air down, and then that gives you time to absorb that noise in the ductwork before it gets to the diffuser. Then there's duct length. Remember, distance is always our friend when we're trying to make something quieter. If we move it away from the source, that's good. And then the path, we get credit for turns and U-turns. We get bounce back from the sound waves, and if they correspond with being out of phase, then we can cancel some of that out. And so just the natural physics and the natural configuration of the ducts allows us to decrease the noise level at the diffuser. We're not going to do a full analysis of ducts. We do that in 520, but what we're going to do is just a single pathway. We're not going to figure in the elbow, and go from there in a couple lectures. And then ductwork material, so liner. If the duct is lined, it can attenuate mechanical noise. It's better at the high frequencies than the low frequencies, which makes sense, right? It's all based on dimension. And then duct wrapping or dampening, and this helps attenuate break-in and break-out noises. The two cans with a string between them, right? And so if a noise jumps into a duct from another space, so what do I mean by that? If you have a duct running across a scene shop and somebody's working in that scene shop and that goes into the auditorium and somebody's running a table saw and you don't have proper wrapping or dampening, or you haven't taken the precautions to build around and isolate that duct, that noise is going to jump into that duct and then it's going to come out on the other end at the diffuser. So we want to avoid that. These are some charts that we're going to look at. So this is flexible duct insertion loss. This is straight insertion. This is not adding sources, so we're not doing log. Let's say we've got a 60 dB source at 125, and we've got 10 feet of flexible duct on it. What did I say? 60 dB. That level would be 59 at the end of that duct. That's just straight addition, subtraction, insertion lost. And then we have rectangular 1 inch, and note that this one is dB per foot. So where this one is length, if it doesn't go over 10 feet, I probably would not use more than 10 feet because the static pressure is probably going to be too high. These are all manufactured data. This is pulled off cut sheets. For rectangular, it's by octave bands. So 2 being 125, 250, 500, 1K, 2K, 4K. So we're in that realm that of NRC, right? We're not looking at 63, and then we're not looking at 8K and 16K on here. 1 inch lined round spiral duct, and then an inlet reflection. So it should be noted that an in reflection on smaller ducts does help attenuate low frequency sounds that are in the duct. And we'll touch on that. We won't figure that in when we're looking at this path, but we will do that in other paths. So we've got flexible duct, round lined, rectangular line, and then we can add in reflection at the end. Flexible duct does well at 500, 1K, 2K, 4K, so we're not going to get much performance at 250 and 125 hertz. So if we have a lot of low end at this point when it comes off the branch duct, we're not really going to attenuate that too much. Basically what it's going to do is you can see these are very thin walls. There's not a lot to them, and so any high level, low frequency just jumps out right out of it. There's no barrier for that, so it doesn't see it in the physics terms from a physical aspect. These allow connections from diffuser to main runs, but they do increase static pressure because they're not straight, they're flexible, and they have bends. So we can't use this all the time. This hence why we limit that to 10 feet. Then you have round duct. Attenuates all octave bands. Pretty decent, but when we look at, notice this high end, these high frequencies over here, and as it gets bigger, it has less attenuation. So at a 48-inch duct, a really massive duct, you've seen these in stadiums, there's no attenuation at 125 really. There's barely any at 250. So if you have an issue, this is why changing the profile of the fan to have more mid frequencies and high frequency sound power, you can deal with it easier with these ducts. Used as main branch ducts and low static pressure. Now remember, we're for a 6-inch, we're at 231, 204 up in the upper frequencies. Rectangular line duct, same, all octave bands, used as main branch runs, and the issue with this is this creates turbulence. So if we go back and look, this looks pretty smooth, and it's going to have nice transitions when you have to make 45s or 90s. This, however, looks a little bit more convoluted. This is just stuck to the sidewalls. There's a little washer on here, and it pushes it in, holds it. So you've got a lot more rough surface that causes turbulence in there, which in turn increases static pressure. You increase static pressure. Your fan needs to be bigger. However, we get a lot of attenuation, almost twice, 3 or 4 times for a 6x6 duct. Relatively the same size, going to have the same speeds, but you've got a lot more at the high end. So it's one thing to keep in your toolbox. So let's look and see if we can solve this problem. This is a real world problem over at the Bastion Theater that it tested out. And when it was measured, it was a 45 NC, which is too high. If you remember performing arts, we want to be 20, 25 on there. And the biggest issue is at 500 hertz. Right, so our curve goes over here, 500 hertz, gets us to 45, and we have a level of 50 dB at 500 hertz. No, it's not the highest level. 250 hertz is the highest level. So when we're looking at this curve, we're assuming that anything that we do up in these bands here, by adding attenuation up in this area, is going to bring these down. And so we want to get to NC25, which is down here. We want to be in this curve. So we want to be down here. We're up here. We want to be down here. We've got a lot to do. So the example of this is if you can't take the main branch ductwork out, could you use after the main branch ductwork to the diffusers? Could you use 1-inch lined, or could you use flexible duct to solve this problem? So if we're looking at 125, we need 6 dB of attenuation. 250 hertz, we need 17 dB. And then 500 hertz, we need 18 dB. And so if we look at this is a blown out chart over here. If we look at what we need for 5-inch flexible duct, 5-inch works. So at 125, we would get 9 dB. If we have 10 feet, we would blow this up. This is the size of the duct, the length of the duct, and then this is octave band 2, which is 125. So 9 would cover that. 17 does not cover, 12 does not cover 17 at 250 hertz. But the 28 would cover the 500 hertz. So now, even though this was the issue before, if we swap out and add 10 feet of ductwork, flexible ductwork from the branch to the diffuser, we're gonna get closer. We're gonna bring this down. We're gonna still need 5 dB at 250 hertz. That's something key to kind of remember. So if we can bring this down, we could get there. We can't do it with just flexible duct. We're outside of it. We need more than 10 feet. So 5-inch of flexible duct's not going to work. What if we did spiral round? And we could add as much as we wanted. So it's not 6.4. Let's change that. Let's change that right now. Put a question mark. That's what it's supposed to be. I don't know where that number is. Must be too late in the day. Now let's go back. Too late in the day. There we go. So how much round duct do we need? Well, it depends. Depends what we're trying to accomplish. So if we're just trying to get rid of 125, we still need 10 feet. And so something to note, solving the problem at 125 and 500 with flexible duct is a lot less expensive than trying to get 6-inch round duct up there. This is a lot harder to fabricate and install. This, you just connect it to the branch. You, for flexible duct, connect it to the branch outlet and then connect it to the inlet of the diffuser, and you're good to go. So we need just over 10 feet, probably a little bit less, because we're not considering end reflection, and we don't have any turns in this. So if we do any of that, we could probably knock this down to 8.6 feet. But at 250 hertz, so if we look at this, it's 0.59. So we have less attenuation at 6-inch, but we need less. We do have a lot more attenuation at 125 or at 250, but we need a lot more. We need 18 feet. And again, we don't have in reflection in here. Um, and we don't have turns. If we added a couple elbows, we could knock 3 dB off of that, get it closer down to 14 or 11 dB, which would mean we would need about 11 feet of ductwork here. So we're still 10 here, still 11 if we consider best case scenario. But if I'm doing a design, I'm going off of 18 feet right now. I want to be more cautious in case I have to give something up on there. And we've got more absorption at 500 hertz. We only need 11 feet. So really the issue that we're looking at now, this is why those single number descriptors don't work, is it's 250 hertz that we have to solve. So if we put in almost 20 feet of 6-inch round line duct, we will solve this problem. We will get this room, this hypothetical situation, real room, but we're using the data a little bit different. We can get this room from a NC45 to an NC25. Now, can we fit 20 feet of ductwork up there? That would be the question. That's what we would look at next. The other option is we can add a silencer, and that silencer can knock down the air handling unit. So if you recall the example that we're using, we've got air handler coming up, ductwork into the room. This is just reversed. Here's the air handler. Above, here's the room. You'll notice we've got some structure that isolates, right? We've got a lot of thick structure. This is why the sections are good to show this. So we've got an air handling unit, and then we've got structure above that isolates that. It's not close to it. And then we bring the duct up, put the diffuser as close to the mechanical equipment as we can get, and then we go out into the space. And what you're really doing, it's not magic, you're just shifting the octaves. So you remember it was much easier to attenuate above 500, 1K, 2K, 4K. So we're adding in some low end attenuation down here. Thing that you need to know also is that this adds power level. So we have to add the power level of this to the self-generated noise power level here, and then we will get the output, convert that over to SPL. We're not going to do that in this class, just noting it so you know what you need to do. There's a bunch of software out there, and we'll look at that at the very last one to do that. We don't need to do these calculations by hand. And that's your level here. What you're trying to do is knock down this low frequency that you can't deal with in a duct in the silencer and bump the high frequency up. That's basically what you're trading off, but you're assuming that high frequency will be absorbed in this duct. So inserted at the source, used for low end attenuation. You'll notice there's kind of a peak at 500, right? It goes up. It's really hard to attenuate the 0, 1 octave bands, right? 31 and a half and 63. And then at 125, we've got some good performance, 250 hertz, right? The one that we had an issue with, this is very good at that. 400, that's usually or 500, band 4. That's the highest, and then it drops back off. So we're not doing a lot of attenuation at the high frequencies. We're going to do that in a line duct. But we need to be aware that it's also producing noise. And the thing to note is usually these are already higher, right? And so if we're outside of 10 dB, we don't add the sources together. So what we're looking at is we come back here, and at 200, or let's use 250 hertz, that's the one we needed. We've got a loss, insertion loss of 22 dB. So if we look at this at 250, and we knock it down 22 dB here, instead of having a 97, we're down to 75, much more manageable, right? and we've gained 22 dB of attenuation. If we're looking at the previous problem, that solves our 250 hertz problem. And then at 1K, 2K, 4K, 8K, we're not really adding to that power level, right? Because we're outside of 10 dB. So we're inducing levels into it, but it's not at the levels of the air handling unit. That's what you want to be key. This is why you want to put them as close together as possible. Now this becomes an issue if you try to put it right before the diffuser, and you're running this much air through it. So you want to be mindful of where you place it on there. So looking at a silencer, if we put a silencer in at over by the air handling unit, we just need a 3-foot silencer. If we have a 3-foot silencer at 250 hertz, we knock out. Let's go to the slow one. Slow it down. So if we're doing supply, that's 250 feet per minute. Right, we've slowed it down a little bit, quite a bit. So we've got insertion loss of 21 at 250, 24 at 500, and then 14 at 125 covers it. So instead of 20 feet of line duct or over 10 feet of flexible duct, we can put in a 3-foot silencer. This is going to be more expensive than the flexible duct. It's going to be on par with 20 feet of line duct installed cost, because you got to get up in the ceiling, you got to take a ceiling down, you've got to suspend it. This you just cut into it over at the air handling unit over at the source. So this is we're looking at what we're saving on this aspect at the 6, 17, 18 dB. So we've got at 250, we're down at 24, 21, and 14. Covers these easily. We wouldn't need to do any of these. That would be overkill. And really, in all actuality, the silencer is a little bit of overkill, but it'd be better on there. If we're just looking at that case, that would bring that down. We'd solve that problem. And then we've got the diffusers. We've got type, size, function, whether it's supply or return, and then what the throw is. So the type, if it's a slot diffuser, everybody likes to put slot diffusers around the side of their room. Well, now you've got to throw across the room. If you have to throw across the room, you have to increase the speed of your air, how fast it's moving, so that throw will work. So if you're looking at a cut sheet here, it's airflow, static pressure, NC. It's horizontal throw, and then it's vertical. So if we look at this, as we add more CFM, we get a further throw, and we also get higher in the NC value. Now the thing to note about picking out diffusers like this, what usually happens is the mechanical will give us the size of the air handling unit, and then they'll ask for what the design criteria is for a space. And if we tell them it's NC 25 space in here, what they're going to do, they're going to go look at their diffuser, see how many diffusers they need, because they haven't had any acoustics anywhere, and they're going to go, okay, well, they said it's 25. Here's a 25 3-slot diffuser, so I need this, and if I have 500 CFM in the room, I'm going to need 10 of these, 11 actually. So I'm going to need 11 of these, and I'm going to spread it out a little bit. So I'm really going to do 15 of these around here at an NC25. I should be good to go. The problem is now we're adding 15 of these noise sources in there. So it's actually not an NC25 for all of them. Because it's 15 sources, we've got to bump that up by 11.8. If we go back and looking at adding dBs on the logarithmic scale on there. So we do have to logarithmically add these together. And so instead of 25, we're at 36.8. which isn't bad, but it's not 25, right? And so if this was a 35 room and they did the same thing and they went and they said, okay, I've got a 35 diffuser and got the same 500, so I can still use 10, right? It's all kind of the same number of which one they need. So 52 CFM, NC35, we add 11.8 to that because they've got, well, we just have to add 10. We don't have 11, or we don't have 15. We just got 10 on here. 10 sources, add 10 dB because they're all the same. We're at a 45. We're back up to the problem that we're trying to solve on there. So we just want to be mindful of what we're choosing on here. That's what I see probably 70% of the time when we have a problem with noise. It's that this was picked out too high. So if we were trying to shoot for a NC 25 in a room, we probably don't want to do this one. We probably want to do this one at 10 CFM, which means we need them all over the place. That's why it's just better in performing arts. You just kind of open it up, slow down the air, and let it fall from the ceiling is the best option. Not getting a lot of turbulence air on there. It's harder to do though because you're not getting that throw on there. And that's the basics. That's the basics of background noise from a mechanical standpoint. If we don't fix that portion of it, we might as well not look at the walls. Might as well not put fuzz on the wall. Might as well not look at the walls for isolation. Look at the surfaces and put fuzz, like the podcast was doing, because the equipment in the room is already too loud. All right. Thanks, and have a great day out there in Radio Land.